Sai Ram. To this last part of our study of adsorption and catalysis, where we have already studied various factors of adsorption and various aspects of catalysis, let us see in this final part the various characteristics that are being associated with catalysis. Generally, you will be aware of this, and it is more about jotting down those aspects of catalytic parts. So let us see some of those parts here then. Let's go with the starting parts, some catalyst characteristics. A catalyst remains unchanged at the end of the reaction. Now, why it's unchanged? It is unchanged because it takes part in the reaction, sees to it that the speed of the reaction is increased, but it is not part of the final product formation. So therefore, you are not going to get any variation for that catalyst in these cases. So this is the one important characteristic that we come across for catalysts. A small quantity of catalyst is generally enough. Now, two words have to be seen here. One is small quantity. This is one phrase. The second one is generally. Now, what does this mean? Smaller quantities indicates that you don't need very high quantities in kgs. Suppose your reactants are used in some kgs, 1 kg, 2 kg. Catalyst you don't need to use in the same quantity. Some grams may be enough, because understand the role of catalyst. What is the role of catalyst? It is not helping in product formation. It is just seeing to it that rate of the reaction is increased. So therefore, minimum quantities are enough, but sometimes it may need large quantities because each molecule may need the effect of catalyst. That is why this word generally is being put up here. That most times it is minimum quantities, sometimes you may need it, that part. So this is about the second characteristic of catalysis. The third one, the catalyst does not alter the position of equilibrium state in a reversible reaction. Now this has to be connected to the equilibrium chapter we have studied, where suppose we had A plus B giving rise to, and this is mainly a reversible reaction we have to consider. So in these cases, we understand that the rate of the forward reaction is equal to rate of backward reaction. This condition we call it as equilibrium. So what does the catalyst do? It still maintains the same equilibrium, just that the speed with which it attains equilibrium, that is been decreased to a large extent, because catalyst sees to it that reactions happen at a faster pace. So this is the third part. Catalysts are generally specific. Now generally specific because you cannot just randomly use catalysts for various reactions. Particular properties of catalysts help in those reactions to undertake at a faster pace. A catalyst cannot initiate a reaction. Now what do you mean by initiation? Initiation means starting. It cannot start a reaction. For starting, you may require reactants, temperature, pressure, everything. What catalyst can do is, once you have started the reaction, it can help in continuity of a reaction and maybe at a pace improvement for the reactions. The activity of catalyst can be increased by the presence of promoters and decreased by the presence of poison. This was the concept that we have studied in the last part. The major importance being given for the role of promoters and poisons. So their role is basically increasing or decreasing the activity of catalysts. So these are certain general characteristics of catalysis that we come across, and a couple of types of catalysis. Let us just see: homogeneous, heterogeneous. I think you are very much aware of these words. Homogeneous indicates similar, and heterogeneous indicates some change. Now what is that factor or criteria of maintaining similarity and change? It is nothing but state of the compounds which are present here. So let us first see the example, then let us go to the things there. We can see that sulfur dioxide is there, oxygen gas is there, and then sulfur trioxide is formed. All this has been done with the support of catalytic property of NO, nitric oxide. You can observe that everybody is gaseous in nature, G, even here and here. So all the people who are involved in this case are in one particular state, either gas, either liquid, either solids, doesn't matter, but everybody has to be in the same state. So this is about production of sulfur trioxide. Similarly, you can see that in the formation of glucose and fructose. In this also, we have seen from sucrose when we form, everybody is in aqueous form. So what do you mean by this condition here is that when the catalyst is present in the same phase. Now what does phase indicate here is the solid, liquid, gaseous or aqueous form. If they are in the same phase, such a type of catalytic reaction we call it as homogeneous catalysis. Exact reverse of this, exact opposite of this you can attribute for heterogeneous catalysis, where when the catalyst is present in a phase other than that of reactants. Just that the catalyst phase is different. You can see an example of the Haber's process in preparation of ammonia. Both these are gaseous in nature, though it's not been notified. All these three conditions are basically gases in nature. And what's the catalyst here? It is solid. Even if you take the promoter molybdenum, that is also solid in nature. But then that is not relevant for this discussion. So here what is important is variation in phases indicates that they undertake heterogeneous catalysis. Similarly, in the contact process, once again you can see that in fact the reactants and products are same. If you see both the example, the first example here, sulfur dioxide, oxygen, sulfur trioxide, the catalyst used is gaseous nitric oxide. Come to the next setup that we have here, it is once again sulfur dioxide, oxygen, sulfur trioxide, but the catalyst used is a little different, which is platinum, and the phase of platinum is solid. So this is how we can differentiate between homogeneous catalysis and heterogeneous catalysis. One important final part that we tend to study for the sake of catalysis is what is the chemical revelation about catalytic properties. No doubt it speeds up the reaction and all, but how does it speed up? It is after all a compound. So what is the chemical aspect of this? This has been attributed to a factor called as activation energy. The word itself says that activate means that you give some amount of energy to that. So what does the catalyst do is, suppose these are the graphical representations that we have. If these are reactants, so I have reactants. Naturally, you need to supply energy for a reaction to happen. So you can see that this is the energy axis that we have shown here, and the x-axis is the reaction coordinate. Now what do you mean by reaction coordinate is basically those components of reactants as well as products. So when reactants get converted to products, naturally when reaction has to happen, you have to supply it some amount of energy. So when you go to supply some amount of energy, the energy component will definitely increase. Because until and unless you supply energy, the reaction is not going to happen. And then if it has to be stabilized into products, it will give away its energy. So you can see that there are actually two graphs which are being denoted here. Now one has been showed for uncatalyzed reaction, the other one is showed for catalyzed. What is catalyst doing here is, it is seeing to it that the energy required for the catalyst to convert reactants into products is reduced. So this is the change in energy that you are seeing. Instead of having so much of energy for conversion of reactants to products, presence of catalyst, it sees to it that the energy requirement is lesser. So this is where you can understand the role of catalyst clearly, that catalyst is not going to form altogether new products, it is not going to form something new out of the way. All it is going to do is increase the speed. And how is it going to increase the speed? It is going to increase the speed by reducing the activation energy which is required. So instead of so much of energy, only this much energy can be enough. So the depiction is shown that EA is the activation energy for a reaction which you don't use catalyst. Then this EA dash, just a representation of sorts, that is considered to be the activation energy required when you use a catalyst. And very clearly it is shown that the catalyst lowers the activation energy. The presence of catalyst brings down the activation energy. So what is the use of bringing down the activation energy? Since it does not need too much of energy for conversion from reactant to product, reaction will happen at a faster pace. So this is how we see the presence of catalysts making a difference in these type of chemical reactions as such. So this is all that we have in this chapter of adsorption and catalysis. Hope you have been able to understand all these aspects, and see you again with a new chapter. Thank you. Sai Ram.